Good morning, students. Today we have to see that random variable. In last class, we are also discussing about random variable, and some of the examples is belongs to random variable. First of all, we are discussing the random variable is totally having the relationship with the probability theory. Already in last class, we are discussing the definition for random variable is we are also calling the random variable is a stochastic variable. The random variable or a stochastic variable is defined as a rule or a relationship with that assigns the real values to each outcome of a random experiment. It is a random variable definition. Here we are having the random variable when after doing the random experiments. How we can define the random variable for a outcomes of one random experiment. You can see that here I am giving that one example for a random variable. The first set can be representing the outcomes of a random experiment. According to definition of random variable, each and every outcome can be mapping to real values like 1, 2, 3, 4, 5. Here, this each and every outcome must be mapping to real values. This mapping process we are calling a random. In that, tossing a coin. When after tossing a coin, the possible outcomes we are having either head or tail. In this case, the head and tail both are having the mutual events. The mutual events means the event occurrence is not any affect another event. Those events we are calling the mutual events. Here, when we are tossing a coin, we are having the total events are one is a head and the second one is a tail. These two are outcomes. The outcomes when we are tossing a one coin, these head and tail. For this case, head and tail we are taking in a one representation or a set representation. Here head and tail we are assigning to real values, like you can give the values are 1 and 2. You can providing the mapping between the outcomes of a sample space. The sample space is containing the all possible outcomes of a random experiment. In this sample space, the events is must be mapping to real values like this. What are the mapping process we are providing? These are the real values. The mapping process between the outcomes of a random experiment and a real values, you are calling it is a random variable. I am repeating the definition once again. The random variable or stochastic variable is defining that it is a rule or relationship that assigns real values each outcome of a random experiment. Can mapping the outcomes to real values. This process we are calling the random variable. Here the random variable is represented with capital letters. The elements in a random variable we are representing with small letters like X, Y, Z, like this. In last class we are seeing one example for a random variable. We are consider car racing. In car racing, the number of participants is a all outcomes of this random experiment. Our desired outcome is which person is winning in this race is our desired outcome. In this race of a game, we are taking each outcome can be representing with lambda suffix I. Here we are not consider those names, we are assigning the real numbers. The reason is why not to consider the probability theory. The numerical nature is very flexible when comparing to descriptive nature. That's why we can take in that each and every person name with numbers. We can assign the numbers by taking the one parameter is a variable parameter lambda I. This lambda I can representing each participant name. each participant name we can assign into real value. The real value is a capital X. Capital X of lambda I is representing the real value. When after assigning the outcomes to real values is calling a random variable. For this random variable representation, generally we are giving that like this, X of lambda I. This one is one of the example for a random variable. Conditions for a function to be a random variable. We are mainly having three conditions when function is calling a random variable. The first condition is the elements in a sample space is not uniquely mapped, but each and every element is must be mapping to one real value. This one is a first condition. I am repeating once again, the first condition when a function is said to be random variable is the elements in a sample space must be not uniquely mapping. That means you can see one example for that. I am taking that outcomes. Outcomes is a sample space. Here the outcomes can be mapping to real values. The real values here only is a -2. Here the relation is providing that the outcomes are not uniquely mapping, but all the elements must be mapping to real values. Must be mapping to real values. This one is the first condition. See one more example for this condition. We can take in that outcomes. Those are the elements of a sample space. We are representing is the x1, x2, x3. And you can assign to these all are to your real values. The real values are -1, 0 and +1. We can mapping this one is x1 to -1 and x2 to +1 and x3 to 0. This one is a unique mapping. According to our condition, more than one outcome may map to a single real value. To a single real value. That can indicate that the more than one outcome is mapping to single real value. This one is the first condition. Not only is a uniquely mapping. This is not like that. We can take anyway. That is, the more than one outcome is having a single real value. This one is a first condition. Coming to second condition. The second condition is we are consider one set. The set is capital X less than or equal to small x. One out to applying the probability to this set value for capital X less than or equal to small x is equal to the sum of individual probabilities of a elementary events. According to this condition, what are the elements in a probability? Suppose you can take in that one set. The set is a capital X less than or equal to small x. Here the capital X is representing random variable and small x is representing the element in this random event. Here, according to this condition, we have considered the probability for this set. The probability of x less than or equal to small x is equal to the sum of the probabilities of all the elementary events corresponding to the set capital X less than or equal to small x. You can see one example here. The example is x is event elements. Those are 1, 2, 3, 4. Those corresponding probabilities is representing in below the 0.25, 0.25, 0.25 and 0.25. Now you can see that according to our condition, here I am writing the probability of capital X less than or equal to 2. Here capital X is a random variable and 2 is a event in this random variable. The event value is must be equal to 2 or less than 2. According to our given data or an example, the given data is starting from 1 to 4 events. it is having the corresponding probabilities is a lesser value of 2 and equal to 2. Those two individual probabilities I am writing here. Those are the probability at x is equal to 1 and the probability x is equal to 2. I am representing those corresponding values is 0.25, 0.25. You can adding these two values, we are getting the final value is 0.5. This one is the second condition. Coming to third condition, the third condition is the probability at minus infinite is 0 and the probability at plus infinite, the value is 1. According to this condition, there is no negative values below the minus infinite. That's why you can consider, you can apply the probability at minus infinite, the value goes to 0. One have to take in that x value is infinite, there is no values beyond the infinite. That's why you can take in that the final value in a probability theory according to Aximov's conditions, the value is 1. One have to consider any function to be a random variable, it must satisfy these three conditions. These three conditions I am writing once again. The first condition is more than one outcome. More than one outcome. More than one outcome. Not uniquely mapping. This one is the first condition, and the second one is we are consider one set. The set is capital X less than or equal to small x. We can take the probability for this set is equal to the individual probability summation value. We are writing that the probability of capital X is equal to x1 plus probability of capital X is equal to x2 plus and so on. We are writing the probability of capital X is equal to up to xn. This one is the second condition. Coming to third condition, the probability at minus infinite, the value goes to 0, and the probability at plus infinite, the value goes to 1. Any function is said to be a random variable, it must satisfy these three conditions. The first condition is more than one outcome, not uniquely mapping. And the second one is when I have to consider the probability for a set is equal to the sum of individual probabilities of a elementary functions. Coming to third one, the third one is that there is no negative values before the minus infinite. That's why you can write that the starting value in a probability is 0. There is no real values after infinite. You can write that in a probability theory the value is 1. Finally, you can say that which function can satisfy these three conditions, those function is said to be a random variable. Now you can see that the types of random variables. What are the types of random variables we are having? We are mainly having three types of random variables. Those are discrete random variable, and a continuous random variable, and a mixed random variable. The first one is discrete random variables. How to define the discrete random variables? The discrete random variables is defining, we can take in the discrete values in a finite interval. The discrete values we are taken from continuous sample space. But what are the examples is relating to discrete random variables? Let's see some examples. So dead, alive, are it dies, and counts. These are some of the examples is relating to discrete random variables. See one more example for a discrete random variable. I want to take in that the pair of two coins, we are tossing the two coins, what are the possible outcomes? For a discrete random variable, I am taking one example. The example, I am consider two fair coins. Two fair coins are tossing. In this case, what are the possible outcomes is available? Here fair means it is having the faces is differently mapping. Suppose one face is head and another face is a tail. For these two fair coins, we are tossing that the possible outcomes we are writing in terms of a sample space. The sample space is containing that the total possible outcomes. The sample space elements are, we are writing the first combination. The first you can toss in one coin, we are getting the head. At the same time, the second coin you are tossing that, we are getting the one more head. Writing the first pair is like this. Head, head. In second time, we can have the same, for first is head and second one is showing like a tail. And next case, the first one is a tail and the second one is a head. In fourth combination, we are taking that both are tails. These four are the total possible outcomes in this event. For this event, my desired outcome is what is the probability for coming of head. Here, the head is the major parameter for my desired outcome. For this outcome, how to writing for a discrete random variable outcomes. Here, my desired outcome is getting the head. Getting the head or a single head. The first pair is head, head. Here we are having that the number of heads are 2. Next one is single head combinations. The single head combinations are, we are having the 2. We are giving that head, tail and tail, head. These two are is mapping to one head. The representation is having only single head, that's why I can have to assign the 1. And third means is a fourth one is both are tails. This pair representation doesn't having head, that's why I can give the indication is 0. This combination tail, tail is 0. Finally, you can writing the discrete random variable is containing the elements is 0 heads and 1 head and 2 heads. This one is a discrete random variable. I am repeating once again. For discrete random variable, we are given the definition is the random variable is having the discrete values in a finite interval is calling discrete random variable. The discrete random variable is obtaining from continuous sample space. Here we are seeing one example. The example is we can take in that two fair coins. You are tossing these 2 coins. What are the possible outcomes is there? In this event, your desired outcome is getting a single head. Getting a single head. Otherwise, what is the possibility for getting the head? For this purpose, we are writing the sample space. The sample space as is equal to what are the possible pairs is appear in this event. First of all, we are writing that both are heads, head tail, tail head, and both are tails. These can be representing like in terms of sample space. Already you know that the sample space is containing the total possible outcomes. Now you can see that our requirement is 1 head. What is the head probability? Here the first case we are having the 2 heads. We are having first one is 1 head and second one is another head. That's why you can give the real number is 2. And second one is single head pairs. The single head pairs is 2 is available. We are writing that head, tail, head. We can give the real values 1. And fourth pair combination is doesn't containing any head, that's why you can give the 0 notation. This one is a first type discrete random variable example. Now you can see the second type. The second type is continuous random variable. The continuous random variable is defined that it is having the infinite values in a finite interval. Infinite values in a finite interval is called the continuous random variable. The continuous random variable is not obtained from discrete sample space. What are the examples they are saying for this continuous random variable is, for example, is a blood pressure and weight. These are a continuously varying with respect to time. You can see that the third one is mixed random variables. The mixed random variables, they are defining that the mixed random variable is a combination of discrete random variable and continuous random variable, which is having the both combination of continuous and discrete. We are calling a mixed random variable. The mixed random variable we are rarely using. These are the mainly 3 types of random variables we are having in types of random variables. You can see that the summary of this one, totally we are discussing about the types of random variables. The first one is a discrete random variable, and second one is continuous random variable, and third one is mixed random variable. Simply remember discrete random variable. The discrete random variable is defining that we can take in the discrete values in a finite interval. The discrete random variable is achieving from the continuous sample space. For continuous random variable, we are defining that it is having the infinite number of values in a finite interval. It is a continuous random variable. The continuous random variable values are not achieving from discrete sample space, but this value is possible in discrete random variable. The discrete random variable values is achieving from continuous sample space. Coming to third one is a mixed random variable. The mixed random variable is a combination of discrete random variable as well as continuous random variable. We are calling the mixed random variable. The mixed random variable we are rarely using. You can see that one example for this mixed random variable is a combination of continuous event as well as discrete event. Suppose we can take in that one spin wheel. The spin wheel is having a continuous values is marked from 0, 3, 6, 9 and 12. Is marking from 0 to 12. At the same time, you can consider one coin. We can perform these two events simultaneously. The final outcome is having one is a continuous values and second one is a discrete values. The combination we are calling a mixed random variable. These are the example to a mixed random variable. Remaining thing, we have to see that in next class.